let yourself find a comfortable position. Feel the weight of your body sinking into whatever surface supports you, each muscle releasing its hold, each breath coming a little slower, a little deeper than the last. Tonight, we're embarking on a journey through deep time, through eons so vast that human civilization becomes nothing more than a brief flicker, a candle flame in an endless night. But this isn't a journey that requires effort or attention. Simply allow the words to wash over you like gentle waves, painting pictures in your mind as you drift toward sleep. We're going to explore a question that sounds like science fiction, but emerges from serious scientific inquiry. What if we aren't the first? What if, millions of years before humans walked upright, before our primate ancestors descended from the trees, before the age of mammals even began, another civilization rose on this very planet? What if they built cities, developed technology, looked up at the same stars we see tonight, and then vanished so completely that we would never know they existed? Close your eyes if you haven't already. Breathe slowly, and let's explore this haunting possibility together. Before we begin, if you find yourself enjoying these journeys into science and relaxation, consider subscribing to the Science Pillow. Each week, we explore fascinating topics from across the sciences, always presented in this calm, soothing manner designed to help you unwind or drift off to sleep. Hit that subscribe button, and if you're feeling generous, tap the like button too. It helps others discover these nighttime explorations of wonder. Your support means we can continue creating these peaceful journeys through knowledge. Now, let the video play, and let yourself fully relax into tonight's story, the question that haunts deep time. There's a peculiar comfort in certainty, isn't there? We like to know our place in the grand scheme of things. Humans, we tell ourselves, are special. We're the first species on Earth to build cities that pierce the clouds, to split the atom, to leave footprints on another world. We look back through the fossil record and see nothing like us. The dinosaurs dominated for 165 million years, yet they never invented the wheel. Trilobites scuttled across ancient seafloors for 270 million years without developing writing. We, in our brief flicker of existence, accomplished what no other creature ever has. We're unique. We're first. But what if that certainty is an illusion? What if our confidence stems not from genuine knowledge, but from the limits of what we can see? The question arrived not from fringe theorists or conspiracy enthusiasts, but from two respected scientists working at the intersection of astrophysics and climate science. In 2018, Adam Frank, an astrophysicist at the University of Rochester, and Gavin Schmidt, director of NASA's Goddard Institute for Space Studies, published a paper with a provocative title, "The Silurian Hypothesis: Would it be possible to detect an industrial civilization in the geological record?" The name came from a British science fiction television series, Doctor Who, which featured an ancient race of intelligent reptiles who built an advanced civilization on Earth millions of years before humanity evolved. Frank and Schmidt weren't seriously proposing that reptilian overlords once ruled the planet, but they were asking a profoundly unsettling question. If such a civilization had existed, how would we know? The answer, it turns out, is both fascinating and terrifying in its implications. We probably wouldn't know, not with any certainty. The Earth, you see, is remarkably good at erasing evidence. It's a vast recycling system, constantly churning, grinding, melting, and transforming everything on and beneath its surface. The planet has been doing this for 4.5 billion years, and it's extraordinarily efficient. Think about what happens to everything we build, everything we create. A wooden house, left abandoned, returns to soil within a few decades. Metal rusts and crumbles. Even concrete, that seemingly eternal substance of our modern world, cracks and breaks down over centuries. The cities we're so proud of, these monuments to human achievement, would be unrecognizable in 1,000 years without constant maintenance. In 10,000 years, most would be completely gone, reduced to scattered fragments buried beneath sediment and vegetation. In 1,000,000 years, virtually nothing recognizable would remain on the surface. But surely something would survive, you might think. Surely there would be signs. Fossils, perhaps. Artifacts preserved in just the right conditions. And yes, that's true. We do find fossils. We've assembled the history of life on Earth from these precious fragments. But here's what most people don't realize. Fossilization is incredibly rare. Consider the numbers for a moment. Scientists estimate that the fossil record captures less than 5% of all species that have ever lived. Less than 5%. That means more than 95% of every creature that ever crawled, swam, flew, or walked on this planet has vanished completely, leaving no trace whatsoever. Their bodies decomposed, their bones dissolved, their existence swallowed by time. And those are just species, entire categories of life forms. When we talk about individual organisms, the odds of preservation drop even further. For an organism to become a fossil, an extraordinarily specific set of conditions must align. The creature must die in just the right place, typically somewhere sediment can quickly bury the body before scavengers tear it apart, or bacteria reduce it to nothing. The environment must be just right, often oxygen poor to slow decay. The sediment must eventually harden into rock without crushing the remains beyond recognition. That rock must survive for millions of years without being melted by volcanic activity, ground up by tectonic forces, or dissolved by groundwater. Then, after all of that, the fossil must be exposed at Earth's surface at a time when humans are around to find it, and someone must actually notice it before erosion destroys it. The odds against any of this happening are astronomical. Most organisms that die simply disappear, their molecules recycled into soil, water, air. Even those that do fossilize might be forever entombed in rock that never sees daylight again, or that does emerge only to be worn away by wind and rain before anyone notices. The fossil record, magnificent as it is, represents only the tiniest fraction of life's full history. It's like trying to reconstruct a 1,000-page novel from a handful of randomly scattered sentences. Now, imagine applying this to technological artifacts. A smartphone, for instance. What would happen to one if it were buried in sediment and left for 10 million years? The glass would dissolve. The plastics would break down, though perhaps not completely. We're still learning about how long some synthetic materials persist. The circuit boards would corrode. The rare earth elements might be scattered or reconcentrated by geological processes. Would anything recognizable remain? Possibly not. Even if some strange amalgam of materials survived, would we recognize it as technology? Or would we classify it as some curious mineral formation, an interesting anomaly, nothing more? The Silurian hypothesis isn't claiming that ancient civilizations existed. Both Frank and Schmidt were clear about that. They wrote explicitly in their paper, "While we strongly doubt that any previous industrial civilization existed before our own, Their goal wasn't to argue for ancient reptile overlords or any other science fiction scenario. Instead, they wanted to explore the limits of our knowledge. They wanted to understand how we might detect traces of industrial activity in the geological record, both here on Earth and potentially on other planets. Because if we can't reliably detect evidence of past civilizations on our own world, how can we hope to find them elsewhere? But in asking this question, they opened a door to a disquieting possibility. We tend to assume that the absence of evidence is evidence of absence. We don't see ancient factories in the rock record, so there must not have been any. We don't find fossilized computers, so nobody built them. But what if we're simply looking at timescales so vast that almost nothing survives? What if the evidence we'd need has been ground to powder, melted, or subducted deep into Earth's mantle? The planet you're lying on right now is not the same planet that existed 100 million years ago. Not in any meaningful physical sense. The continents have moved thousands of miles. Mountains have risen and been worn flat. Ocean floors have been created and destroyed. Entire landscapes have been buried under miles of sediment or thrust up from the deep to become new mountain ranges. The very atoms that make up the rocks beneath your feet have been cycled through Earth's interior multiple times, melted and reformed, their histories erased and rewritten. Earth's surface is constantly being recycled. The oldest surface on Earth, a stretch of desert pavement in Israel's Negev desert, is only about 1.8 million years old. Only 1.8 million years. That's nothing on geological timescales. The oldest rocks we've found are billions of years old, but they've been buried, heated, compressed, altered beyond recognition from their original forms. The surface itself, the ground we walk on, rarely persists for more than a few million years in any recognizable state. This is what plate tectonics does. The planet's outer shell is broken into massive plates that drift atop a layer of partially molten rock. These plates collide, creating mountain ranges. They pull apart, forming new ocean basins. They slide past one another, generating earthquakes. And, critically, they dive beneath each other at subduction zones, where oceanic crust plunges back into Earth's interior to be melted and recycled. Every square inch of ocean floor on Earth is less than 200 million years old. All of it. The older stuff has been dragged down into the mantle and destroyed. Now think about what this means for the preservation of evidence. If a civilization arose, say, 250 million years ago, during the Permian period when the supercontinent Pangaea was forming, where would their cities be now? If they built on what was then coastline, those locations are now deep beneath the ocean floor, or they've been subducted and melted. If they built inland, their locations have since been folded into mountain ranges, buried beneath sediment layers miles thick, or worn away completely by hundreds of millions of years of erosion. The ground they walked on no longer exists at Earth's surface. It's been recycled, transformed, incorporated into new rocks. This is the challenge that Frank and Schmidt highlighted. Earth is ancient, but Earth's surface is young. The stage is constantly being reset, and in that resetting, almost all evidence of what came before is erased. Not because of some conspiracy, not through any malicious intent, but simply because that's what planets do. They churn, they change, they forget. So we return to the question, how would we know? If some other civilization rose and fell millions of years before us, how would we detect their existence? The answer Frank and Schmidt arrived at is both clever and somewhat unsettling. We wouldn't look for cities or artifacts. Those would almost certainly be gone. Instead, we'd look for chemical and isotopic signatures in the geological record, anomalies that might indicate industrial activity. We'd look for the kinds of changes that civilization inevitably produces. But to understand what we'd look for, we first need to understand what we know about Earth's deep past and how we know it. We need to journey back through time, through layers of rock and sediment, to periods when the world was unimaginably different from today. And we need to understand just how difficult it is to read the Earth's story, written in stone, the fragility of evidence. To understand how completely evidence can vanish, we need to understand what Earth does to everything on and beneath its surface. We need to understand the processes that make fossilization so rare, and that make preservation of technological artifacts even rarer. Let's begin with the simplest question. What happens to a body after death? When an organism dies, nature immediately begins the process of decomposition. Bacteria, already present in the gut and on the skin, multiply rapidly, breaking down tissues from the inside out. Scavengers, from vultures to beetles to microbes, consume what they can. Larger predators might drag a carcass away and scatter the bones. Weather does its work. Rain washes away soft tissues. Freezing and thawing break down cellular structures. Sunlight bleaches and weakens organic molecules. In most environments, a dead animal is reduced to scattered, fragmentary bones within weeks or months. Within years, even those bones begin to break down, their minerals dissolving into soil. For fossilization to occur, something must interrupt this process. The most common scenario is rapid burial. A creature dies in or near water, a river, a lake, the ocean. Sediment, perhaps stirred up by a storm or flood, quickly buries the body. This accomplishes several crucial things. It protects the remains from scavengers that can't dig through sediment. It creates a low-oxygen environment where the bacteria that cause decay work more slowly, and it provides a stable environment where the slow process of fossilization can begin. Fossilization comes in many forms. Sometimes the original material is preserved with little change. Bones are already mineralized, made of calcium phosphate, so they can persist if conditions are right. But usually, groundwater seeping through the sediment brings dissolved minerals that gradually replace the original material. Calcium carbonate, silica, iron minerals. These infiltrate the bone's structure, molecule by molecule, replacing organic material with stone. The process can be so gradual and so fine-grained that it preserves microscopic details of cell structure. We can see individual bone cells in fossils hundreds of millions of years old. But this requires an extraordinary chain of fortunate circumstances. The sediment must eventually harden into rock, but not so quickly or with so much pressure that it crushes the fossil. The rock must remain buried at a depth where temperatures and pressures don't exceed the limits of fossil preservation. Too deep, and the rock metamorphoses, transforming under heat and pressure into something new, destroying any fossils within it. The rock must avoid being melted by volcanic activity or ground up along fault zones. It must survive millions or tens of millions of years. Then, and only then, erosion or tectonic uplift must bring the rock back to Earth's surface at a time when creatures capable of recognizing fossils exist. And someone must actually find the fossil before it weathers away. A fossil exposed at the surface lasts decades, perhaps centuries before erosion destroys it. in the grand scheme of geological time, this is nothing. Most fossils are probably eroded away before anyone sees them. Given all of these constraints, it's remarkable that we find any fossils at all. The paleontologist Jack Horner once estimated that we've found fossils representing perhaps 1 in 10,000 species that ever lived. Others suggest the fraction is even smaller. The fossil record is not a complete archive. It's a collection of lucky accidents, a scattering of moments when everything aligned just right. Now, consider what this means for preserving evidence of civilization. Buildings are made of materials selected because they resist decay, at least on human timescales. Stone, brick, concrete. These persist longer than wood or organic materials. But how much longer? We have ruins of ancient civilizations spanning thousands of years. The pyramids of Egypt are about 4,500 years old and still recognizable, though weathered and plundered. Roman buildings, 2,000 years old, survive in various states of preservation, but extend the timescale. Imagine a building left alone for 1,000,000 years. The roof fails first, within decades. Rain enters. Water is the great destroyer. It seeps into cracks, freezes and expands, wedging stones apart. It dissolves minerals, particularly the calcium carbonate in limestone and concrete. It allows vegetation to take root. Tree roots are extraordinarily powerful. They can crack massive stones. Within centuries, a building without maintenance begins to collapse. Within millennia, it's a pile of rubble. The rubble itself continues to break down, stones splitting and crumbling, until after tens or hundreds of thousands of years, there's nothing recognizable left. Just scattered fragments mixed with soil. What about materials we think of as more durable? Metals corrode. Iron rusts. Copper oxidizes. Even supposedly noble metals like gold, while they resist corrosion, can be dissolved by certain natural chemical processes over long enough timescales. Stainless steel, aluminum, titanium. These might last longer, but even they eventually succumb. And crucially, most metal objects are relatively small. A corroded metal artifact, buried and transformed, might be indistinguishable from a natural mineral formation. Glass, made from silica, should theoretically last a very long time. Sand is essentially tiny fragments of silica, and it's among the most stable materials on Earth's surface. But glass is also brittle. It shatters. The fragments get smaller and smaller until they're indistinguishable from natural sand. And on geological timescales, even glass can devitrify, changing from its smooth, amorphous state to a crystalline form that looks like any other rock. Plastics are where things get interesting. These synthetic polymers are so new that we don't have millions of years of data on how they break down under geological conditions. In the environment we do observe, sunlight and bacterial action slowly degrade plastics over decades to centuries. But some plastics seem remarkably resistant to breakdown. Microplastics persist in soil and water. If buried in sediment away from sunlight and oxygen, plastics might last much longer. Future paleontologists might find a plastic layer in rock strata from the Anthropocene. But would they recognize it as the product of technology? Or would they classify it as some unusual organic-rich sediment? The most durable artifacts might be the smallest and most abstract, chemical signatures. When we burn fossil fuels, we release carbon that's been locked underground for hundreds of millions of years. This carbon has a specific isotopic composition, depleted in carbon-13 compared to carbon from other sources. That distinctive isotope ratio gets recorded in sediments laid down during the period of fossil fuel combustion. It's a signature of our industrial activity. Similarly, nuclear weapons testing in the mid-20th century scattered radioactive isotopes across the planet. Plutonium-244, a synthetic element that doesn't occur naturally on Earth, can be detected in sediments and ice cores. Its presence is unambiguous evidence of nuclear technology. But plutonium-244 has a half-life of 80 million years. After a few 100 million years, it would have decayed to undetectable levels. And this raises a crucial point. How long do signatures persist? Carbon isotope anomalies can be detected in rocks hundreds of millions of years old, like those from the Paleocene-Eocene thermal maximum. But those anomalies have natural explanations that don't require invoking ancient civilizations. Could we distinguish a natural carbon spike from one caused by fossil fuel combustion millions of years after the fact? Maybe not with certainty. What about more direct evidence? The oldest human artifacts are stone tools dating back about 3.5 million years. Humans didn't invent stone tools. Other hominids before us used them. But they're recognizable as tools because of their shape and the pattern of wear on their edges. Stone is durable. These tools survived being buried, being moved by geological processes, being exposed at the surface again. But they survived in part because they're recent. A stone tool from 100 million years ago, if it somehow avoided being destroyed by plate tectonics, would likely be so worn and altered that we'd have difficulty distinguishing it from a naturally broken rock. And this brings us to one of the most sobering facts about Earth's surface: how young it is. Researchers studying the Negev desert in Israel found what they believe is the oldest continuously exposed surface on Earth. Using a technique called cosmogenic nuclide dating, which measures the accumulation of rare isotopes produced when cosmic rays strike rocks. At the surface, they determined that this desert pavement has been exposed for about 1.8 million years. 1.8 million years sounds like a long time. It predates anatomically modern humans. It goes back to a period when our ancestors were Homo erectus, barely recognizable as related to us. But on geological timescales, it's nothing. It's less than 1/20 of 1% of Earth's history. The oldest rocks on Earth, found in Canada and Australia, date back more than 4 billion years. But those rocks have been buried, heated, uplifted, buried again, metamorphosed, folded, fractured, and generally subjected to every transformative process Earth's interior can inflict on them. They have been recycled through the rock cycle multiple times. The oldest surface, though? A mere 1.8 million years. The implication is stark. Almost no surface older than a few million years remains exposed on Earth. Everything older has been buried under sediment, subducted into the mantle, or eroded away. The ground beneath your feet is young. It's new. It's been recycled from older materials, melted and reformed and rearranged countless times. Plate tectonics is the mechanism behind this recycling. Earth's rigid outer layer, the lithosphere, is broken into pieces called tectonic plates. These plates drift atop the partially molten asthenosphere beneath them, moving at rates of a few centimeters per year. That doesn't sound fast, but over millions of years it adds up. Continents that were joined separate and drift thousands of kilometers apart. Ocean basins open and close. Mountains rise and are worn flat. At divergent boundaries, plates pull apart. Magma rises from the mantle to fill the gap, creating new oceanic crust along mid-ocean ridges. At convergent boundaries, plates collide. When two oceanic plates meet, one typically subducts beneath the other, diving back down into the mantle where it melts. When continental plates collide, neither subducts easily. Continental rock is too buoyant, so instead they crumple, forming mountain ranges like the Himalayas. This system means oceanic crust is constantly being created and destroyed. The oldest ocean floor on Earth is only about 200 million years old. Everything older has been subducted and melted. 200 million years sounds ancient, and it is by human standards. But life has existed on Earth for at least 3.5 billion years. Complex, multicellular life has existed for over 500 million years. If a civilization arose on land adjacent to an ocean and built their cities on what is now oceanic crust, those sites have been destroyed, ground up in subduction zones, and recycled into magma. Continental crust fares better. It's thicker and more buoyant, so it doesn't subduct easily. The oldest continental rocks date back more than 4 billion years, but even continental crust isn't immune to transformation. Mountains are thrust up by tectonic forces, then worn down by erosion. The Appalachian Mountains in eastern North America were once as tall as the modern Himalayas. That was about 480 million years ago. Now they're worn down to mere shadows of their former grandeur, gentle peaks that wouldn't impress anyone familiar with the Rockies or the Alps. Given enough time, even the Himalayas will be ground flat. Sediment from eroding mountains accumulates in basins, often along continental margins. Layer upon layer builds up, burying whatever lies beneath. The weight of accumulating sediment compresses the layers below, driving out water and cementing particles together into rock. If something is buried in these sediments, a fossil, an artifact, anything, it gets locked into the rock. But it doesn't stay there forever. Tectonic forces might later uplift that rock, exposing it to erosion again. The cycle continues endlessly. Uplift, erosion, deposition, burial, lithification, uplift again. This is the rock cycle, and it ensures that Earth's surface is in constant flux. Rocks formed in one era can be destroyed and reformed in another. Evidence buried in sediment can be metamorphosed beyond recognition or melted entirely. The planet forgets. Not intentionally, not maliciously, but simply through the relentless operation of physical processes that have been grinding away for eons. So, when we ask whether evidence of an ancient civilization could survive, we must confront these processes. Could buildings survive plate tectonics? Not if they were located where oceanic crust formed or subducted. Not if they were buried beneath miles of sediment and subjected to the heat and pressure of deep burial. Not if they were caught in tectonic collision zones and ground up in mountain building. Could artifacts survive? In theory, yes, if they were in just the right location and made of just the right materials. A few scattered objects buried in stable continental crust, in rock formations that avoided the worst of tectonic activity, might persist for hundreds of millions of years. But finding them would require extraordinary luck. We'd have to drill or excavate in exactly the right location. We'd have to recognize what we'd found, and we'd have to do all this before erosion destroyed the evidence. The odds are not favorable. The Earth is very good at keeping secrets. It's very good at erasing the past. And this means that our certainty about being first must be tempered with humility. We know that no civilization like ours existed in the recent past within the last few million years. We'd see evidence. But beyond that, beyond the reach of the youngest surface rocks, our knowledge fades into uncertainty. Breathe deeply. Let this settle over you like a blanket. The vastness of geological time, the impermanence of everything, even stone, the humbling recognition that Earth remembers very little of its long history. We think of rock as eternal, but it's not. It's just slow. Everything changes. Everything is eventually recycled. And in that recycling, the past vanishes, leaving only the faintest traces for those who know how to look. Reading Earth's faint whispers. If direct evidence of ancient civilizations is likely lost to geological processes, what remains? How might we detect the ghost of a civilization millions of years after it vanished? This is where chemistry becomes our ally. This is where we turn to the subtle language written in isotopes and elemental abundances, the faint whispers that persist even when the structure that created them is long gone. Consider what our civilization does to the planet's chemistry. We extract materials from deep underground and bring them to the surface. We mine coal, oil, natural gas, all products of ancient life buried and transformed over millions of years. We dig up metal ores, concentrating elements like copper, iron, aluminum, rare earth elements. We move billions of tons of rock each year, more than all of the world's rivers combined. We synthesize completely new molecules that never existed in nature. We split atomic nuclei and create radioactive isotopes that would never form naturally on Earth's surface. All of these activities leave signatures, chemical fingerprints that get recorded in sediments accumulating in lakes, oceans, and other depositional environments. These sediments eventually become rock, and the signatures become frozen in time, waiting for future geologists to discover them. The most obvious signature is carbon. When we burn fossil fuels, we release carbon dioxide into the atmosphere. This carbon comes from plants and plankton that died millions of years ago, converting atmospheric carbon dioxide into organic matter through photosynthesis. When these organisms were buried and transformed into coal, oil, or natural gas, they locked that carbon away underground. But here's the key. This ancient organic carbon has a distinctive isotopic composition. Carbon comes in 3 isotopes: carbon-12, carbon-13, and carbon-14. Carbon-12 is the most common, making up about 99% of all carbon. Carbon-13 is stable but less abundant, about 1%. Carbon-14 is radioactive and decays over time, making it useful for dating relatively recent organic material, but irrelevant for ancient geological studies because it all decays away within tens of thousands of years. The ratio of carbon-13 to carbon-12 varies depending on the source of the carbon. Plants preferentially use carbon-12 during photosynthesis because it's slightly lighter and easier to incorporate into organic molecules. This means organic matter, and the fossil fuels derived from it are depleted in carbon-13 compared to other carbon sources like limestone or atmospheric carbon dioxide. When we burn fossil fuels and release their carbon into the atmosphere, we're adding carbon-12-rich carbon. This shifts the overall isotopic ratio of atmospheric carbon, making it more negative, meaning relatively less carbon-13 compared to carbon-12. This shift gets recorded in any organisms or minerals that incorporate atmospheric carbon. Trees record it in their growth rings. Ocean-dwelling plankton record it in their shells. Sediments accumulating on the ocean floor preserve it. Future geologists examining rock layers from our time will see this isotopic excursion. This distinctive shift toward more negative carbon isotope values, coinciding with a massive spike in total atmospheric carbon. They'll know that something released a lot of carbon-13 depleted carbon in a geologically short period. If they don't know about us, they might attribute it to a natural cause. Massive volcanic eruptions, perhaps, or the destabilization of methane deposits. But they'll see the signature clearly. Now, here's where the Silurian hypothesis becomes relevant. When we look back through the geological record, we do see carbon isotope excursions. The Paleocene-Eocene thermal maximum is the most famous, but it's not unique. There are others scattered through time, periods when carbon isotope ratios shifted dramatically, accompanied by warming and other environmental changes. The PETM occurred about 56 million years ago, at the boundary between the Paleocene and Eocene epochs. Over a period of several thousand years, global temperatures rose by 5 to 8 degrees Celsius. Ocean chemistry changed dramatically. Many deep-sea organisms went extinct, while new species appeared. And in rocks from this period, we see a pronounced negative carbon isotope excursion. Estimates suggest that between 3,000 and 20,000 petagrams of carbon were released into the atmosphere. Scientists debate what caused the PETM. The leading hypothesis involves volcanic activity. The North Atlantic was a hotbed of volcanism around this time, as Greenland began separating from Europe, forming the North Atlantic Ocean. Massive volcanic eruptions could have released enormous amounts of carbon dioxide. Another hypothesis involves methane hydrates, ice-like solids that form in cold ocean sediments under high pressure. If ocean temperatures warmed slightly, perhaps due to orbital changes or initial volcanic carbon release, these methane hydrates could have destabilized, releasing methane that oxidized to carbon dioxide, causing further warming in a runaway feedback. These are plausible, natural explanations, and most geologists accept them. But Frank and Schmidt pointed out the uncomfortable similarity between the PETM and what our industrial civilization is doing. Both involve massive carbon release with a distinctive isotopic signature. Both cause rapid warming. If future geologists knew nothing about us and examined the Anthropocene boundary, they might propose similar natural explanations for our carbon spike. The question, then, could the PETM have been caused by an industrial civilization? Almost certainly not, for several reasons. The carbon release at the PETM occurred over several thousand years, much slower than our fossil fuel combustion. The total amount, while large, is within the range of what volcanic or methane hydrate releases could produce. And there's no evidence of other industrial signatures coinciding with the PETM. No unusual concentrations of metals, no synthetic materials, no radioactive isotopes. But, and this is the crucial point, the similarity shows how difficult it would be to distinguish certain natural events from industrial activity based solely on carbon isotopes. If a civilization existed, burned through its fossil fuel reserves over a few thousand years, and then collapsed, the carbon signature they left might be indistinguishable from a natural event. We'd need additional evidence to make the case. What other signatures might we look for? Nitrogen isotopes present another possibility. Modern agriculture uses synthetic nitrogen fertilizers produced through the Haber-Bosch process, which converts atmospheric nitrogen into ammonia. This process creates nitrogen with a specific isotopic signature. Widespread use of such fertilizers would shift the nitrogen isotope ratios in soil and runoff, which would get carried to oceans and recorded in sediments. A future civilization looking at our time period would see this shift. An ancient civilization using similar technology might have left a similar signature, though millions of years of diagenesis, chemical changes in sediment as it turns to rock, might obscure it. Rare earth elements offer another avenue. These elements, despite their name, are actually relatively common in Earth's crust. But they're dispersed, never concentrated enough in one place to form miniable ores under most circumstances. Modern technology relies on rare earth elements for everything from smartphone screens to wind turbines to electric car batteries. We mine these elements, concentrate them, and use them in ways that might leave unusual patterns in the geological record. A spike in rare earth concentrations in sediments from a particular time period, distributed globally rather than locally, might suggest industrial activity. But again, distinguishing this from natural geological processes would be challenging. Then there are the radioactive signatures. Natural radioactive isotopes exist throughout Earth's crust: uranium, thorium, potassium-40. But certain isotopes only form in nuclear reactions. Plutonium-239, for instance, doesn't occur naturally on Earth in any appreciable quantity. It forms in nuclear reactors and nuclear weapons. Its presence in sediments from the mid-20th century onward is unambiguous evidence of nuclear technology. Plutonium-239 has a half-life of 24,000 years. After a few 100,000 years, the amount remaining would be vanishingly small. Other plutonium isotopes, like plutonium-244, have longer half-lives, 80 million years, but even these would decay to undetectable levels after several half-lives, roughly a few 100 million years. An ancient civilization that used nuclear technology might have left plutonium signatures, but only if they existed relatively recently in geological terms, within the last few 100 million years. Beyond that, the evidence would decay away. Other potential signatures include changes in ocean chemistry recorded in the shells of marine organisms. Industrial pollution affects ocean pH, making it more acidic. This gets recorded in the calcium carbonate shells of plankton and other organisms. Ancient ocean acidification events do show up in the geological record, but they're usually attributed to natural causes like volcanic carbon release. Again, ambiguity. We might look for anomalous concentrations of certain synthetic organic molecules. Some plastics, if they survive millions of years, might leave distinctive chemical signatures. Organic pollutants like PCBs and dioxins are entirely synthetic and have unique molecular structures. But organic molecules break down over time, especially under heat and pressure. After millions of years in rock, would any survive in recognizable form? It's unclear. The most robust signatures would likely be those that affect global geochemistry in ways that are difficult to explain through purely natural processes. For instance, a thin layer enriched in iridium spread globally in sediments from 66 million years ago provided key evidence for the asteroid impact that killed the dinosaurs. Iridium is rare in Earth's crust, but more common in asteroids. Its global distribution in a thin layer was the smoking gun that convinced most scientists of the impact hypothesis. Similarly, if an ancient civilization conducted global-scale industrial activity, we might find a thin layer with unusual chemical or isotopic compositions spread around the world. But here's the problem. How do we know what's unusual? We have one example of industrial civilization to compare against: ourselves. We don't have a large statistical sample of what industrial civilization signatures look like. An alien geologist examining Earth might recognize our signature as anomalous. But would we recognize a different civilization's signature if it didn't look exactly like our own? This is the fundamental challenge. The rock record is full of anomalies, unusual chemical spikes and isotopic excursions and periods of rapid environmental change. Most have natural explanations, but some remain mysterious, not well understood. The end Permian mass extinction, about 252 million years ago, saw the greatest die-off in Earth's history. 96% of marine species went extinct. The cause is still debated. Massive volcanic eruptions in Siberia are the leading suspect, but the exact mechanisms that caused such extensive extinction remain unclear. Could an industrial civilization have contributed? Almost certainly not. The evidence points strongly to volcanism and its consequences. But the point is that we're still discovering new aspects of Earth's history, still finding events we don't fully understand. The Silurian hypothesis doesn't claim that any of these mysterious events were caused by ancient civilizations. It simply asks, how would we know? What would constitute proof? And the honest answer is, we're not entirely sure. We'd need multiple independent lines of evidence converging on the same conclusion. A carbon isotope excursion alone wouldn't be enough. But an isotope excursion combined with unusual metal concentrations, plus synthetic molecules, plus radioactive signatures, all coinciding in the same narrow time window, that would be harder to explain naturally. Of course, finding such evidence would be extraordinarily difficult. The rock record is incomplete. We have only examined a tiny fraction of all the rock strata on Earth. Most of the geological record is buried inaccessibly deep, or has been destroyed by plate tectonics. The portions we can study represent a biased sample, favoring certain types of rocks deposited in certain environments. And even if we found something suspicious, interpreting it would be fraught with difficulty. Science is conservative, and rightly so. Extraordinary claims require extraordinary evidence. Proposing that an anomalous chemical signature was created by an unknown ancient civilization would require ruling out all plausible natural explanations. Given how little we still understand about many geological processes, definitively ruling out natural causes might be impossible. So we're left with uncertainty. We can search for signatures. We can study anomalies in the rock record. But unless we find something truly unambiguous, a fossilized computer chip, perhaps, or a layer of synthetic polymers, we probably can't prove an ancient civilization existed. And conversely, the absence of evidence, given how poorly evidence preserves over millions of years, doesn't prove they didn't exist. It's a strange position to be in. We're forced to acknowledge the limits of our knowledge. We look at Earth's deep past and admit, there are things we cannot know, mysteries that might remain forever mysterious. The planet has forgotten, and we cannot make it remember. Rest in that uncertainty for a moment. Let it wash over you. Not knowing can be uncomfortable, but it can also be oddly peaceful. We don't have to have all the answers. The universe is vast, deep, ancient beyond our comprehension. Some secrets might remain hidden forever, and that's okay. We do what we can. We search, we study, we piece together what fragments we find. But we also accept that some questions might not have definitive answers. And in that acceptance, there's a kind of quiet relief. When could they have existed? If we entertain the possibility of ancient civilizations on Earth, even as a thought experiment, we must ask, when could they have arisen? What periods in Earth's history might have allowed for the evolution of intelligence and the development of technology? The answer requires us to journey back through deep time, through eras so remote that the world was unrecognizable, yet also to confront the constraints that biology and evolution impose. Earth formed about 4.54 billion years ago from the disk of dust and gas surrounding the young sun. For perhaps the first few 100 million years, our planet was a hellish place, still hot from its formation, bombarded constantly by asteroids and comets left over from the solar system's birth. The Moon formed during this period, probably from debris thrown into orbit when a Mars-sized object crashed into proto-Earth in a cataclysmic impact. Gradually, the planet cooled. Oceans condensed from water, vapor in the atmosphere. The late heavy bombardment, a period of intense asteroid impacts around 4 billion years ago, represented the final major assault before things settled down. Life appeared remarkably quickly after conditions became habitable. The oldest evidence for life dates back at least 3.7 billion years, possibly as far as 4.3 billion years. These earliest organisms were simple, single-celled, probably similar to bacteria. For roughly 3 billion years, life remained at this level of complexity. Bacteria and archaea, those ancient single-celled organisms, dominated. They fundamentally transformed Earth through their metabolic processes. Cyanobacteria, for instance, evolved photosynthesis and began releasing oxygen as a waste product, slowly building up atmospheric oxygen over hundreds of millions of years. But they built no civilizations. They had no technology. Complex, multicellular life, the kind we're familiar with. Animals, plants, fungi, appeared much later. The first multicellular organisms show up in the fossil record around 2 billion years ago, but they remained simple for a long time. The real explosion of complex multicellular life occurred during the Ediacaran period, starting about 635 million years ago, and especially during the Cambrian explosion about 540 million years ago, when most major animal body plans appeared within a relatively short span of geological time. But multicellular life alone doesn't give you civilization. The vast majority of species that have ever existed were not intelligent in any meaningful sense. Intelligence, as we understand it, the ability to solve novel problems, to create tools, to transmit knowledge across generations, to manipulate the environment in sophisticated ways, is rare. On Earth, only a few lineages have evolved what we might call higher intelligence. Certain primates, including humans. Some cetaceans like dolphins and whales. Some birds like crows and parrots, possibly octopuses, though they're so different from us that comparisons are difficult. And of these intelligent creatures, only one has developed technological civilization: us. This suggests that the path to civilization is narrow, requiring a very specific combination of traits and circumstances. You need intelligence, yes, but you also need the ability to manipulate objects precisely. Hands or something equivalent. You need social structures that allow knowledge transmission and cooperation. You need environmental pressures that favor innovation. You need enough time for evolution to work its slow magic, building layer upon layer of adaptation. And you need, frankly, a lot of luck. So when we ask when ancient civilizations could have existed, we're really asking, when could something like humans have evolved? The answer depends on several factors, but primarily on when complex multicellular life capable of evolving intelligence first appeared. The Ediacaran fauna, those strange soft-bodied creatures from 600 million years ago, were complex but probably not intelligent. They lacked obvious sense organs, brains, limbs. They appear to have been mostly immobile or slow-moving filter feeders and grazers, not promising candidates for evolving civilization. The Cambrian explosion changed things. Suddenly, animals with eyes, brains, grasping appendages, active, predatory lifestyles appeared. Trilobites scuttled across the seafloor. Anomalocaris, a fearsome predator over a meter long, hunted with grasping appendages and compound eyes. Here were creatures with nervous systems, with the ability to process information about their environment and respond dynamically. Could intelligence have evolved from such a foundation? Theoretically, yes. Trilobites, for instance, existed for nearly 270 million years, from the Cambrian through the Permian. They diversified into thousands of species, adapted to nearly every marine environment, developed increasingly sophisticated eyes. If the pressures had been right, if some lineage had moved onto land and developed the ability to manipulate objects, if, could there have been a trilobite civilization? Almost certainly not, but the question illustrates the point. Once complex animal life existed, the biological machinery necessary for intelligence existed. Nervous systems could be elaborated. Senses could be refined. Behaviors could become more complex. Evolution had the raw materials. But evolution doesn't have goals. It doesn't aim for intelligence. Intelligence only evolves if it's advantageous, if it helps organisms survive and reproduce in their particular environment. For most of Earth's history, most environments, intelligence wasn't particularly advantageous. Being bigger helped. Being faster helped. Being well-armored helped. Having more efficient metabolism helped. But being smart? That only helps in specific circumstances. Primates evolved intelligence, we think, in response to the challenges of living in complex social groups and navigating arboreal environments. Tool use initially evolved for relatively simple tasks, and only gradually became more sophisticated. Humans didn't spring fully formed from the evolutionary tree. We're the product of millions of years of incremental changes, each step building on the previous one. So, if we ask when non-human intelligence could have evolved on Earth, we need to identify periods when the conditions might have been right. Periods when complex animals existed, when ecological niches existed that might favor the evolution of intelligence, when enough time had passed for evolution to work. The first terrestrial animals appeared about 430 million years ago. Plants had colonized land slightly earlier, creating ecosystems that animals could exploit. The first land animals were probably arthropods similar to millipedes. Later came amphibians, evolving from fish. Then reptiles evolved from amphibians, developing the ability to lay eggs on land, freeing them from dependence on water. The Carboniferous period, from about 360 to 300 million years ago, saw vast forests of primitive plants and enormous arthropods. Millipedes grew to over 2 meters long. Dragonfly-like insects had wingspans of 70 centimeters. Oxygen levels were high, possibly as much as 35% of the atmosphere compared to today's 21%, which allowed arthropods to grow large despite their inefficient respiratory systems. Could intelligent arthropods have evolved during the Carboniferous? It's hard to say. Arthropod nervous systems are quite different from vertebrate nervous systems. Some modern arthropods, like jumping spiders and mantis shrimp, show surprisingly sophisticated behaviors and possibly some form of consciousness. But they're small, their brains limited by the constraints of their exoskeletons. The giant arthropods of the Carboniferous were impressive, but we have no evidence they were particularly intelligent. Reptiles diversified during the Permian period, 299 to 252 million years ago. Then came the Triassic, when dinosaurs first appeared, followed by the Jurassic and Cretaceous, the famous age of dinosaurs. Dinosaurs ruled the Earth for about 165 million years. Some were enormous, the largest land animals ever to exist. Others were small and agile. Some hunted, others grazed, and some, particularly certain theropods, the group that includes Tyrannosaurus rex but also birds, showed signs of relatively sophisticated behavior. Troodon is the name that appears most often in discussions of dinosaur intelligence. This small theropod lived during the late Cretaceous, about 76 million years ago, in what is now North America. It stood about a meter tall and stretched roughly 2 meters long, weighing perhaps 60 pounds. Not imposing by dinosaur standards. But Troodon had something special, a brain-to-body size ratio that rivaled modern birds. Scientists calculate something called an encephalization quotient, or EQ, which measures how large an animal's brain is relative to what would be expected for an animal of its body size. Most dinosaurs had low EQs. The giant sauropods, those long-necked herbivores like Diplodocus, had EQs around 0.2. Their tiny brains were dwarfed by their massive bodies. Stegosaurus, with its famously small brain, had a similar ratio. But Troodon? Recent estimates suggest an EQ around 5.8, placing it in the range of modern ratites, large flightless birds like ostriches, and potentially approaching the lower range of mammalian intelligence. Now, EQ is an imperfect measure. Brain size alone doesn't determine intelligence. Structure matters. Neuron density matters. The specific organization of different brain regions matters. But a large brain, relative to body size, does suggest the potential for complex behaviors. And Troodon showed other signs of sophistication. Its eyes were large and forward-facing, providing binocular vision and depth perception essential for hunting active prey. Its hands were grasping, with curved claws suitable for clutching small animals or eggs. Fossil evidence suggests it engaged in brooding behavior, sitting on nests of eggs much like modern birds do, indicating parental care. Some paleontologists propose it may have been omnivorous, eating both meat and plants, which would suggest behavioral flexibility. And, perhaps most intriguingly, some evidence hints that Troodon may have been nocturnal, hunting at night when other predators were less active, relying on its keen senses to navigate and hunt in darkness. Could something like Troodon have evolved higher intelligence if given enough time? In principle, yes. The raw materials were there. A relatively large brain, grasping appendages, sophisticated sensory abilities, complex behaviors. Evolution doesn't march toward intelligence as a goal, but if environmental pressures favored ever greater cognitive abilities, perhaps through complex social interactions, or tool use, or ecological challenges requiring problem-solving. Then, over millions of additional years, Troodon's descendants might have evolved brains rivaling or exceeding those of modern primates. But they didn't get that time. 66 million years ago, an asteroid roughly 10 kilometers across struck the Yucatan Peninsula in what is now Mexico. The impact released energy equivalent to billions of nuclear weapons. It threw up vast quantities of dust and debris into the atmosphere, blocking sunlight and causing global cooling. Wildfires raged across continents. Acid rain fell. The food chain collapsed. Within a geologically brief period, perhaps just decades or centuries, 75% of all species on Earth went extinct, including all non-avian dinosaurs. Troodon died out along with Tyrannosaurus, Triceratops, and all the other giants of the Cretaceous. Only birds, small feathered theropods that had evolved flight, survived among the dinosaurs. And with the non-avian dinosaurs gone, mammals inherited the Earth. Small, nocturnal creatures that had lived in the dinosaurs' shadows suddenly had vast ecological niches opening to them. They diversified rapidly, growing larger, adapting to every environment. Within 10 million years, mammals had spread across the planet in forms ranging from tiny shrews to whale-sized herbivores, and eventually, 65 million years after the asteroid impact, one lineage of mammals would evolve the intelligence to ask questions about deep time. But imagine a different history. Imagine the asteroid missed. Imagine dinosaurs continued to dominate for another 66 million years, or 100 million, or 200 million. With that much time, could intelligence have evolved among them? Could some descendant of Troodon, or perhaps some other clever theropod, have developed the ability to make tools, to use fire, to build shelters, eventually to create technology? It's impossible to say with certainty. Evolution is not predictable in detail. The specific path life takes depends on countless random factors: mutations, environmental changes, chance events, extinction. But we can say that intelligence is possible. It evolved at least once in us. The fact that it happened at all suggests it can happen, given the right circumstances and enough time. And therein lies the unsettling possibility. Dinosaurs ruled for 165 million years. That's an enormously long time, much longer than mammals have dominated. If intelligence could evolve in mammals over the past 66 million years, why couldn't it have evolved in dinosaurs over 165 million years? Especially given that some dinosaurs, like Troodon, already showed promising cognitive abilities. We have no evidence that it did. We found no dinosaur tools, no structures built by intelligent dinosaurs, no signs of civilization in the Mesozoic era. But remember the fragility of evidence. Remember how unlikely it is for artifacts to survive millions of years, let alone tens or hundreds of millions of years. If a dinosaur civilization existed, say, 100 million years ago, during the Cretaceous, what would remain? Their cities, if they built any, would be long gone, ground to dust by erosion and plate tectonics. Their artifacts would have corroded or fossilized beyond recognition if they survived at all. Their remains would be subject to the same low odds of fossilization that affect all organisms. We've found only a tiny fraction of all dinosaur species that existed, and most of those from just a few individuals. The fossil record is not comprehensive. It's fragmentary in the extreme. So we return to the central, uncomfortable question. Could we rule out a dinosaur civilization? Based on our current knowledge and the fossil record we have, we can't definitively prove one never existed. We'd need to rely on those subtle chemical signatures, those isotopic anomalies in rock layers from the Mesozoic. And we'd need to be very careful in our interpretations because natural processes can create similar signatures. The thought feels strange, doesn't it? Science fiction has long imagined intelligent dinosaurs, but always as fantasy, never as serious possibility. Yet, when we examine the question rigorously, we can't dismiss it entirely. We can say it's unlikely. We can say we have no positive evidence for it. But we can't say it's impossible. And the window of possibility extends much farther back than the dinosaurs. Complex life has existed for over 500 million years. That's 500 million years during which, in principle, intelligence could have evolved. Not in every period, not under all circumstances, but given the right conditions, the right evolutionary pressures, the right amount of time. It's possible. The Cambrian explosion occurred about 540 million years ago. Before that, life was simpler, mostly single-celled or simple multicellular forms. But after the Cambrian, complex animals with nervous systems, eyes, appendages existed. From that point forward, the biological machinery necessary for evolving intelligence was present. 500 million years ago, during the Cambrian itself? Probably not. Life was still relatively simple, confined to the oceans, experimenting with basic body plans. But 100 million years later, during the Devonian period, often called the Age of Fishes, more plausible, complex ecosystems existed. Some creatures ventured onto land. Intelligence requires challenges, ecological niches where being smart conveys advantage. These conditions were beginning to appear. Move forward to the Carboniferous, 350 million years ago. Vast forests covered the land. Insects and other arthropods thrived in enormous forms. Early reptiles were diversifying. Could intelligence have arisen then? Perhaps. The building blocks were there, and so it continues, period after period, era after era, each representing tens of millions of years, each potentially a window during which intelligence could have evolved, built civilizations, and then vanished, leaving almost nothing behind but the faintest chemical whispers in rock layers that we might never recognize for what they are. This is the true scope of the Silurian hypothesis. Not that ancient civilizations definitely existed, but that we cannot definitively rule them out across vast stretches of Earth's history. The planet is old, life is old, and the evidence we require to reconstruct the past is tragically, frustratingly incomplete. What would remain after millions of years? Let's conduct a thought experiment. Imagine human civilization ends tomorrow. No catastrophic event, no nuclear war, no asteroid impact. We simply vanish. Every person gone in an instant. What happens next? The first changes occur immediately. Power plants stop operating within hours or days, their automated systems failing without human intervention. Lights go out across the planet. Within weeks, without heating and cooling systems, most buildings begin to deteriorate. In climates with freezing winters, pipes burst. In humid regions, mold takes hold. Vegetation begins reclaiming urban spaces remarkably quickly. Grass pushes up through cracks in pavement. Trees send roots into building foundations. Within a decade, most wooden structures have begun serious decay. Roofs collapse. Windows shatter. The elements pour in. Metal structures fare somewhat better, but rust never sleeps. Steel frame buildings in coastal areas, battered by salt spray, corrode faster than those inland. But even inland, rain provides all the moisture oxidation needs to slowly convert refined iron back into iron oxide, essentially rust. The process takes decades, but it's relentless. A century passes. Small buildings have largely collapsed. Even large structures show severe deterioration. Concrete, that modern miracle material, begins to fail as the steel reinforcement bars within it rust, expand, and crack the concrete apart from the inside. Glass windows, those that haven't already shattered, begin to cloud and weaken. The great cities of our time start looking like ruins from ancient civilizations. 1,000 years. Very little remains recognizable. The pyramids of Giza, built of solid stone blocks with no steel reinforcement, might still be there, though weathered and perhaps partially collapsed if earthquakes have struck. But modern skyscrapers? Gone, reduced to rubble buried under vegetation. Metal has largely corroded away. Plastics, surprisingly durable in some environments, break down into ever smaller fragments. Microplastics infiltrate soil and sediment worldwide, but the recognizable forms of bottles and bags and containers vanish. 10,000 years. This is about as far back as recorded human history extends. The oldest known writing, Sumerian cuneiform on clay tablets, dates to roughly this period. Yet, if we disappeared 10,000 years ago, virtually nothing we built would still be visible today. A few stone structures might survive, like the Great Pyramid or massive stone monuments, but everything else? Erased by time, buried under sediment, worn away by weather, consumed by rust and rot and the patient grinding of geological processes. Now extend the timeline further. 100,000 years, 1,000,000 years, 10 million years. The timescales become so vast that they lose meaning to our human minds, but these are the timescales relevant to the Silurian hypothesis. What would remain of our civilization after such spans? Almost nothing directly recognizable. Cities would be buried beneath sediment layers meters or tens of meters thick. In geologically active regions, they'd be folded into mountain ranges or subducted beneath tectonic plates. In stable regions, erosion would wear down any remaining structures to scattered fragments. The tallest mountains would be worn flat, given enough time. Our buildings, far softer than solid rock, would vanish much faster. But let's consider specific materials and what might become of them. Plastics, those ubiquitous synthetic polymers that define modern life, have surprising staying power in certain conditions. When buried in sediment away from oxygen and sunlight, plastics degrade much more slowly than when exposed at the surface. Some plastic objects, particularly in landfills or deep ocean sediments, might persist in recognizable form for thousands of years, perhaps tens of thousands. But millions of years? The chemistry becomes uncertain. We've only been making plastic for about a century, so we don't have direct evidence of how it behaves over geological timescales. However, plastics are organic polymers, chains of carbon-based molecules. Over millions of years, subjected to heat and pressure as sediments are buried and compacted, these polymers would likely break down. The process is similar to what happened to ancient organic matter, dead plants and plankton, that became fossil fuels. Plastics might themselves transform into something resembling oil or solid organic residue. The forms of plastic objects could potentially be preserved as trace fossils. Picture a plastic bottle buried in fine and grained sediment. The plastic eventually breaks down, but the cavity it occupied remains, perhaps filled with other minerals. A future paleontologist might find this oddly shaped void in rock and recognize it as artificial, or they might classify it as some strange natural formation. Without context, without knowing what to look for, would they understand what they'd found? Metals present their own challenges for long-term preservation. In nature, pure metals are rare. Most metals exist as ores. minerals where the metal is chemically bound to oxygen or sulfur or other elements. Refining metal, extracting pure iron or copper or aluminum from ore, requires energy. We're essentially creating something thermodynamically unstable. Given time, metals want to return to their oxidized, lower energy states. Iron rusts into iron oxide. Copper oxidizes into green copper compounds. Aluminum, despite its apparent resistance to corrosion, only survives in modern environments because it forms a thin protective oxide layer. Over geological timescales, subjected to varying conditions of moisture, temperature, and chemical environment, even aluminum would eventually corrode. But metals don't simply vanish. They transform. A steel beam, over millions of years, might become a streak of iron-rich minerals in sedimentary rock. Would a future geologist recognize this as artificial? Possibly not, unless the concentration or distribution of the metal was somehow anomalous compared to natural deposits. A layer of globally distributed metal particles might be detectable as unusual, but scattered local concentrations might not stand out. Copper wiring, that vast network threading through our modern world, represents billions of miles of refined metal. Over millions of years, this copper would corrode and dissipate. But copper is actually somewhat resistant to decay. Ancient copper artifacts, like those from Bronze Age civilizations thousands of years old, survive in recognizable form when buried in the right conditions. A copper object buried in dry, stable sediment might persist for hundreds of thousands of years, perhaps even millions, before chemical processes finally broke it down completely. Gold, that precious metal we value so highly, is among the most stable elements. Gold resists oxidation better than almost any other metal. Gold artifacts from ancient civilizations survive virtually unblemished. A gold ring buried for 10,000 years emerges looking nearly new. So gold might survive millions of years in recognizable form, especially if buried in stable sediments. But here's the challenge. Gold objects are small and scattered. Earth's crust is vast. The odds of future explorers finding a gold artifact among quadrillions of tons of rock is vanishingly small unless they know where to look. And even if they found it, would they recognize it as artificial rather than a natural gold nugget? Glass, made primarily from silica, sand essentially, should theoretically be stable over geological time. Sand persists for billions of years. But glass is amorphous silica, lacking the crystal structure of natural minerals. Over very long timescales, particularly if subjected to heat or chemical action from groundwater, glass can devitrify, transforming into crystalline minerals. A glass bottle buried for 1,000,000 years might transform into something that looks like any other mineral formation. The smooth, formed shape might be preserved, or it might not, depending on conditions. Ceramics and concrete have better odds. These materials are already essentially artificial rock, created by heating or chemically binding minerals. Pottery shards from ancient civilizations survive for thousands of years. Concrete, while it does decay, particularly if reinforced with steel that rusts, can persist for very long timescales when buried. The Roman Colosseum, built with concrete nearly 2,000 years ago, still stands, though heavily worn and partially collapsed. But would ceramics or concrete from our era be recognizable after millions of years? Possibly, if they were buried in the right conditions and later exposed. But distinguishing artificial concrete from natural cemented sediments might be difficult without chemical analysis. The presence of certain additives in modern concrete, Specific ratios of calcium, silicon, aluminum might provide clues, but only if someone thought to look for them. Then there are the truly durable substances. Graphite, the carbon form used in pencil lead, can persist for billions of years. It's essentially pure carbon arranged in a particular crystal structure, and it's chemically stable under a wide range of conditions. Diamonds, another carbon form, are even more stable. A synthetic diamond created in a laboratory is virtually indistinguishable from a natural diamond, and would last essentially forever in geological terms. Certain synthetic minerals created in industrial processes might also persist. We've created over 200,000 synthetic mineral types that don't exist in nature. Some of these, particularly those created under high temperature and pressure to be inherently stable, could survive millions of years. But again, recognition is the problem. A synthetic crystal mixed among natural minerals might not be distinguishable without detailed analysis. Nuclear waste deserves special mention. The radioactive isotopes produced in nuclear reactors and weapons remain dangerous for tens of thousands to millions of years, depending on the specific isotope. Plutonium-239, for instance, has a half-life of 24,000 years. After 10 half-lives, 240,000 years, the amount remaining would be about 1/1000th of the original quantity, but still detectable with sensitive instruments. Some fission products have even longer half-lives. Iodine-129 has a half-life of nearly 16 million years. In principle, our nuclear waste could leave a detectable signature for tens of millions of years, possibly longer. This might be one of the more enduring marks we leave on the planet, ironically through our most dangerous technology. But even radioactive signatures have limits. After enough time, hundreds of millions of years, even long-lived, isotopes decay to undetectable levels. And if the waste containers fail and the radioactive material disperses, it might become so diluted in Earth's crust that it's indistinguishable from naturally occurring radioactive elements like uranium and thorium. What about the marks we've made on the landscape itself? We've reshaped Earth's surface dramatically through mining, construction, agriculture. We've moved more rock and soil annually than all natural erosion processes combined. We've created artificial valleys and hills. We've diverted rivers and drained lakes. Surely these would leave traces. Some might. A massive open-pit mine, a kilometer across and hundreds of meters deep, might leave a distinctive depression that persists for millions of years, especially if it later fills with sediment in a way that creates unusual stratification. But erosion is powerful. Given enough time, it wears away mountains. A pit, even a large one, would eventually fill and be obscured. The truly large-scale changes we've made, deforestation, desertification, species extinctions, would be hardest to detect directly. A forest that we cleared would regrow if humans vanished. Within centuries, the forest would return. Within thousands of years, it might be indistinguishable from an undisturbed forest. The genetic bottlenecks we've created in species through hunting and habitat destruction might be detectable through careful analysis of evolutionary patterns. But that requires a level of sophistication we can barely imagine. Perhaps the best preserved evidence would be in places we haven't touched much. Deep ocean sediments and ice cores. The deep ocean floor, in abyssal plains far from land, accumulates sediment slowly and steadily. Objects that sink there can be buried and preserved. Our ships, once they corrode, would leave scattered metal concentrations. Our ocean dumping of radioactive waste would leave detectable signatures. Microplastics would be incorporated into sediment layers, potentially creating a distinctive plastic horizon in the geological record. But ocean floor, remember, is recycled through subduction. The oldest ocean floor on Earth is only about 200 million years old. Anything deposited on ocean floor older than that has been dragged into subduction zones and destroyed. So ocean sediments only offer a window of a few 100 million years at most. Ice cores from Antarctica and Greenland preserve incredibly detailed climate records going back hundreds of thousands of years. Trapped air bubbles in ice contain atmospheric samples from the past. Industrial pollutants, radioactive fallout, changes in carbon dioxide concentration, all are preserved in ice. But ice eventually melts or flows and compacts, destroying the layering. The oldest ice on Earth is only about 1 million years old. Beyond that time scale, ice is not a reliable archive. This brings us to perhaps the most enduring potential repository of our artifacts, the Moon. The Moon has no atmosphere, no weather, no plate tectonics. Objects left on the lunar surface are affected by micrometeorite impacts and solar radiation, which slowly degrade materials. But the process is far slower than on Earth. The footprints left by Apollo astronauts in lunar regolith will persist for millions of years before micrometeorite bombardment erases them. The landing stages of the Apollo lunar modules, left behind on the Moon, are made of aluminum and other materials. They'll corrode very slowly in the lunar environment. In theory, they could remain recognizable for billions of years. If humans vanished, and an alien civilization or future terrestrial intelligence visited the Moon millions of years hence, they might find our artifacts there, better preserved than anything on Earth. But finding them would require looking in exactly the right locations. The Moon's surface area is about 38 million square kilometers. The Apollo artifacts occupy tiny patches within that vast expanse. Without knowing where to look, you'd never find them. You might map the entire lunar surface at high resolution and still miss them, interpreting them as unusual rock formations or small meteor impact sites. This is the fundamental problem with detecting ancient civilizations through artifacts. Even if something survives, even if it's preserved in pristine condition somewhere, finding it requires knowing where to look. And if you don't know what you're looking for, you might not recognize it even if you find it. So we return to chemical signatures. These diffuse throughout the environment and get recorded in sediments globally. A carbon isotope excursion appears in marine sediments worldwide. Radioactive fallout settles across continents. Unusual concentrations of synthetic chemicals might be detected in scattered locations. These signatures don't require finding a specific artifact. They require only analyzing rock cores from the right time period. But interpreting these signatures requires understanding what caused them. And if you don't know that industrial civilizations are possible, if you've never seen one, you might attribute every anomaly to natural processes. After all, Earth is geologically active. It has volcanic eruptions, impact events, massive landslides, climate shifts, all producing chemical signatures in rocks. Adding one more set of signatures from an extinct civilization to the mix doesn't necessarily make them obvious. The Silurian hypothesis forces us to confront this uncertainty. We look at Earth's geological record and see what we expect to see, what we've been trained to interpret as natural processes. But could we be missing signals? Could there be evidence of ancient industrial activity hiding in plain sight, dismissed as natural because we never thought to question that assumption. We can't say for certain, and that's profoundly unsettling for a species that likes certainty, that likes to know its place in the grand scheme of things. We want to believe we're first, we're special, we're unique. The possibility that we might not be, that we might be following in invisible footsteps laid down by creatures we can't even imagine across timescales that obliterate all memory, is uncomfortable. Close your eyes for a moment. Picture the slow erosion of everything we've built. See cities crumbling and being swallowed by forests. Watch metal rusting, plastic fragmenting, glass clouding. See mountains rising and falling, continents drifting, oceans opening and closing. See the relentless grinding of geological time reducing everything to scattered atoms redistributed through Earth's crust. See our most enduring monuments transformed, buried, lost. See deep time erasing almost all trace that we ever existed. And then imagine this has happened before. Imagine other builders, other thinkers, other civilizations rising and falling in the deep past, their works ground to dust so thoroughly that we'll never know they existed. Imagine them looking up at the same stars we see, asking the same questions we ask, never knowing that others had asked them before, never knowing that others would ask them again millions of years hence. It's a humbling thought, and perhaps a useful one. Our civilization feels so important, so permanent, so significant. But in the context of deep time, we're barely a whisper, a brief flicker of organization in an otherwise mostly empty cosmos. Whether we're first or not, whether others came before or not, our time here is brief. The monuments we build will fall. The works we create will crumble. And if we're very, very lucky, we'll leave behind chemical signatures that a future intelligence might notice and wonder about. But even those signatures will eventually fade. Given enough time, even isotopes decay. Even the most stable chemicals disperse. 1 billion years from now, 2 billion, 3 billion, will any trace of us remain? Almost certainly not. Earth itself might not remain, at least not in a form we'd recognize as the sun swells into a red giant and eventually dies. Deep time swallows everything. Civilizations, species, continents, mountains, even the very rocks that record their passing. Everything returns to atoms, redistributed, recycled, reformed into new configurations that bear no memory of what came before. And yet, in the brief time we have, in this momentary flicker of awareness between vast eternities of non-existence, we ask questions. We wonder. We explore. We try to understand our place in the cosmos. And that impulse, that curiosity, might be one of the most remarkable things in the universe, whether we're the first to experience it or the latest in an endless succession of questioning minds. The implications for life beyond Earth. The Silurian hypothesis started as an exercise in understanding how we might detect ancient industrial civilizations in Earth's geological record. But its implications extend far beyond our own planet. If we can't reliably detect past civilizations on the world we know best, the world we've studied most intensively, what does that mean for our search for intelligence elsewhere in the universe? The search for extraterrestrial intelligence, or SETI, has been ongoing for decades. We've pointed radio telescopes at the stars, listening for artificial signals that might indicate technological civilizations. We've sent messages outward, hoping someone might receive and respond. We've analyzed the chemical compositions of distant exoplanet atmospheres, looking for biosignatures, gases like oxygen and methane that, in combination, suggest living processes. But all of these approaches assume we're looking for civilizations that exist now, broadcasting signals we can detect, altering their atmospheres in ways we can measure. What if most civilizations are already extinct? What if intelligence arises and then disappears within time frames that are brief on cosmic scales? Consider the numbers. The universe is about 13.8 billion years old. Our Sun is only about 4.6 billion years old, relatively young for a star. Many stars in the galaxy formed billions of years before our Sun did. If planets are common, and we now know they are, with virtually every star hosting at least one planet, then Earth-like worlds have existed for perhaps 10 billion years or more. That's an enormous amount of time for life to arise, for evolution to work, for intelligence to emerge. If intelligence is even remotely common in the universe, we'd expect thousands or millions or even billions of civilizations to have arisen over cosmic history. And yet, we see no signs of them. No radio signals. No megastructures dimming distant stars. No evidence of vast engineering projects reshaping solar systems. The universe appears silent, empty of intelligence except for us. This is the Fermi paradox, named after physicist Enrico Fermi, who famously asked, "Where is everybody?" If intelligent life is common, we should see evidence of it everywhere. The fact that we don't demands explanation. Many solutions have been proposed. Perhaps intelligence is extraordinarily rare, requiring such an unlikely sequence of events that it almost never happens. Perhaps life itself is rare. Perhaps planets like Earth are rare. Perhaps there are great filters, challenges so difficult that most life never passes them. Maybe the origin of life itself, or the evolution of complex cells, or the development of intelligence, or the transition to technological civilization. Or perhaps the great filter lies ahead of us. Perhaps civilizations inevitably destroy themselves shortly after developing technology, through nuclear war, environmental collapse, artificial intelligence gone wrong, or some other catastrophe we haven't imagined. If most civilizations last only a few centuries or millennia after becoming technological, and if they're scattered across billions of years of cosmic history and billions of light years of space, we'd never overlap with them. We'd never see their signals because by the time we existed and started looking, they'd already be gone. Their transmissions faded to silence. The Silurian hypothesis adds another layer to this puzzle. Not only might civilizations be separated in time, they might be undetectable even if we could visit their home worlds. If a civilization existed on a planet billions of years ago, built cities, developed technology, and then went extinct, what would remain? If Earth is any guide, very little. Over billions of years, plate tectonics would recycle the planet's crust multiple times. The atmosphere would change. Climates would shift. Impacts, volcanic eruptions, ice ages would reshape the surface repeatedly. By the time we arrived, even if that planet had once hosted a civilization, we might find no evidence of it whatsoever. Think about what this means for astrobiology. We're developing increasingly sophisticated techniques to study exoplanets. We can detect their atmospheres, measure their temperatures, even map weather patterns on some worlds. In the coming decades, we'll build the telescopes powerful enough to detect biosignatures, signs of life, in exoplanet atmospheres. But biosignatures indicate life that exists now or existed very recently. If a planet hosted a biosphere billions of years ago that then went extinct, we wouldn't detect biosignatures in its current atmosphere. We'd see a barren world and move on. never knowing what we'd missed. Could we detect technosignatures, signs of past technology on distant planets? Perhaps if we could examine their geology in detail, a layer of plastic in their rock record. Isotopic anomalies, suggesting industrial activity. Unusual concentrations of refined metals. But getting that level of geological detail from planets many light years away is far beyond our current capabilities. We can barely resolve continents on the nearest exoplanets. Analyzing their geological layers is science fiction, at least for now. This suggests a sobering possibility. The galaxy might be littered with dead civilizations, their remains ground to dust on worlds we'll observe and dismiss as lifeless. We might be surrounded by cosmic ruins and never know it. Mars presents an intriguing case. It's close enough that we can study in detail, and we've sent rovers to analyze its rocks directly. Mars had liquid water on its surface billions of years ago. It had a thicker atmosphere. Conditions might have been suitable for life, possibly even complex life, though we have no evidence of this yet. If life arose on Mars, could it have evolved intelligence? Could Mars have hosted a civilization billions of years ago when Earth was still mostly ocean and simple cells? In principle, yes. The timeline allows for it. And if such a civilization existed and then vanished as Mars lost its atmosphere and water, what would remain? Probably very little recognizable from orbit, but possibly something detectable if we knew where to dig. Unusual chemical signatures in rock layers from the right period. Concentrations of refined materials. Geometric patterns in buried structures. This is purely speculative, of course. We have no evidence of past Martian civilizations. But the point is, we can't rule it out based solely on our orbital observations and the limited surface exploration we've conducted so far. As we explore more of Mars, as we dig deeper and analyze more rocks, we might keep the possibility in mind. Not expecting to find ancient ruins, but willing to recognize them if they somehow survived. More likely, we'd find chemical anomalies, if anything at all. And interpreting those anomalies correctly would require considering non-natural explanations, which science is generally reluctant to do without compelling evidence. The broader implication is that the universe might be far more filled with past life than we realize. Current life existing now, might be relatively rare. But if life arises readily and then usually goes extinct, the cumulative total of life that has existed across cosmic history could be enormous, even if very little of it exists at any given moment. Imagine a galaxy where life arises on a planet every few million years, somewhere in that galaxy. Each instance of life evolves, perhaps develops complexity, possibly even intelligence, and then goes extinct or reverts to simpler forms. At any given moment, only a tiny fraction of planets host life. But over billions of years, life might have appeared on millions of planets, maybe more. We'd be looking for a needle in a haystack, trying to find the few planets where life happens to exist now. And if we're specifically looking for intelligent life, technological civilizations that are broadcasting signals, we'd be searching for an even smaller subset, those civilizations that exist now and happen to be using technologies we can detect. It's like trying to catch lightning. Civilizations might flash briefly into existence and then vanish, and unless you're looking at exactly the right place at exactly the right time, you miss them entirely. The universe might be full of lightning flashes we never see because we're looking at the wrong patch of sky or the wrong moment in time. This has profound implications for SETI strategy. Currently, we focus on searching for signals from civilizations that exist now. But maybe we should also look for signs of past civilizations. Not just listening for radio signals, but searching for technological relics in our own solar system. On the Moon, on Mars, in the asteroid belt, anywhere that might preserve artifacts better than Earth does. Some scientists have proposed exactly this. The archaeological SETI approach suggests we should search for artifacts left by hypothetical ancient visitors to our solar system. An alien probe passing through millions of years ago might have left something behind. The Moon's surface, stable and uneroded, would be an ideal place to look. So far, we've found nothing. Our surveys of the Moon, while detailed, haven't covered every square meter. Small artifacts could remain undiscovered. But the larger point is that we're beginning to think about detection strategies that account for time as well as space, that recognize civilizations might be separated by eons as well as light years. Another implication involves how long civilizations last. We tend to assume, perhaps optimistically, that if civilization can get through its early dangerous phase, avoiding nuclear war, solving climate change, managing artificial intelligence, preventing pandemics, it might last for a very long time. Millions of years, perhaps. We imagine mature civilizations spreading across solar systems, engineering stars, building Dyson spheres, becoming visible across vast distances. But what if that's wrong? What if there's something inherently unstable about advanced civilization? What if technological societies always collapse within thousands or tens of thousands of years, no matter how advanced they become? The causes could vary. Resource depletion, environmental degradation, war, social breakdown, evolution of values that make complex civilization unsustainable. But the result would be the same. Brief flickers of technological activity, followed by long stretches of non-technological existence or extinction. If this is true, it explains the Fermi paradox neatly. We don't see other civilizations because they don't last long enough to become visible across interstellar distances. By the time their signals reach potential receivers, the civilizations are already gone. And the signals themselves fade and disperse, becoming undetectable across cosmic distances and timescales. It also suggests we might be in danger. If other civilizations consistently failed to sustain themselves, why would we be different? What makes us think we can solve problems that might be fundamentally unsolvable? This is a dark thought, admittedly, but it's one we should perhaps take seriously as we navigate challenges like climate change and nuclear proliferation. On the other hand, maybe some civilizations do survive and expand, but they transcend in ways that make them undetectable to us. Perhaps they upload their minds into computers and effectively disappear from the physical world. Perhaps they discover physics we haven't imagined and leave our universe entirely. Perhaps they deliberately choose to remain hidden, avoiding contact with younger civilizations for reasons we can't fathom. These are speculations, of course. But the Silurian hypothesis reminds us that absence of evidence isn't always evidence of absence. Just because we don't see other civilizations doesn't mean they never existed. It might simply mean we're not looking in the right way, or at the right time, or we're not recognizing what we see. As you drift toward sleep, let your mind wander among the stars. Imagine distant worlds orbiting distant suns, some barren, some teeming with life, some silent ruins of civilizations long dead. Imagine the vast loneliness of space, the enormous gulfs between stars, the even more enormous gulfs of time that might separate one civilization's rise from another's. We're floating through a universe that might have seen countless minds awaken and wonder, just as we wonder. We might be surrounded by ghosts, the faint traces of others who asked the same questions, built the same monuments, dreamed the same dreams, and then faded into the deep time that eventually claims everything. Or we might be alone, the only questioning minds in a cosmos of blind matter and energy. We don't know which possibility is stranger or more unsettling. Both are humbling in their own ways. What we do know is that our time is brief. Whether we're first or last or somewhere in between, we have this moment, this brief span of awareness in which to wonder and explore and try to understand. That's precious. That's worth treasuring. And perhaps that's enough. Living with uncertainty. We've journeyed through deep time, through the possibilities and limitations of geological memory. We've confronted the uncomfortable truth that Earth forgets, that almost all evidence of past existence is erased by the relentless operation of geological processes. We've considered that we might not be first, that others might have risen and fallen before us, leaving no trace we can definitively recognize. Now we must sit with that uncertainty, because this is not a mystery with a clear answer, at least not yet, and perhaps not ever. Science deals in evidence. We observe, we measure, we test hypotheses against data. The strength of science lies in its willingness to change conclusions when new evidence arrives, its commitment to following the data wherever it leads. But science also requires evidence to work with. And when evidence has been destroyed by time, when the geological record is too fragmentary and transformed to read with certainty, science reaches its limits. This doesn't mean we stop investigating. Researchers continue to study geological anomalies, to develop new techniques for detecting subtle signatures in ancient rocks, to refine our understanding of how Earth transforms materials over deep time. Each advance in our knowledge might reveal new possibilities or rule out old ones. But it does mean we must cultivate intellectual humility. We must acknowledge what we cannot know. The absence of clear evidence for ancient pre-human civilizations doesn't prove they never existed, only that we haven't found convincing proof they did. And, given the improbability of such proof surviving across tens or hundreds of millions of years, this shouldn't surprise us. Some will find this uncertainty disturbing. We want answers. We want to know our place in the grand scheme of things. The possibility that there are questions we can't definitively answer, mysteries that might remain mysterious forever, feels unsatisfying. But there's another way to view uncertainty, as an invitation to wonder. The fact that we don't know everything, that the universe still holds secrets possibly beyond our reach, makes it more interesting, not less. A cosmos that we fully understood, that held no mysteries, would be a poorer place. The unknown gives us something to explore, something to dream about, something to inspire our curiosity. Consider what the Silurian hypothesis actually does. It doesn't claim ancient civilizations existed. It asks, how would we know if they did? And, in asking that question, it reveals the limits of our knowledge and the assumptions we make often without realizing we're making them. We assume we're first because we don't see evidence of others. But we've now examined that assumption carefully and found it rests on fragile foundations. The geological record is incomplete. Fossilization is rare. Earth recycles its surface. Over millions of years, almost everything is erased. Given these facts, the absence of artifacts proves very little. This is a valuable lesson that extends beyond the specific question of ancient civilizations. In many areas of knowledge, we confidently assert things based on absence of contrary evidence, without carefully considering how likely that contrary evidence would be to survive and be detected even if it existed. The Silurian hypothesis teaches us to be more thoughtful about such reasoning. It also teaches us about perspective. We think of human civilization as enormously significant, a pivotal development in Earth's history. And in some ways it is. No other species has reshaped the planet as we have, but in the context of deep time, our significance shrinks. Earth has existed for 4.5 billion years. Life has existed for at least 3.5 billion years. Complex life has existed for over 500 million years. Our species, Homo sapiens, has existed for about 300,000 years. Our industrial civilization for about 300 years. We're newcomers, extremely recent arrivals on a planet that has hosted life for eons. And if we vanished tomorrow, Earth would continue. Life would continue. In a few million years, new species would evolve to fill the niches we left empty. In 10 million years, our impact would be subtle at best. In 100 million years, almost all trace of us would be gone. This perspective can feel nihilistic. If we're so insignificant in the grand scheme of things, why does anything we do matter? But that's the wrong conclusion to draw. Yes, in the context of deep time and cosmic scales, our civilization is brief and small. But to us, living in this moment, it's everything. The meaning and significance of our lives comes from our experience, not from how we appear to hypothetical observers billions of years hence. The fact that our monuments will crumble doesn't mean we shouldn't build them. The fact that our names will be forgotten doesn't mean our lives lack meaning. We create, we love, we explore, we wonder, not for eternal recognition, but because these activities have value in themselves, in the experience of doing them. And perhaps there's even something beautiful in impermanence. The fact that nothing lasts forever, that even stars eventually die and galaxies eventually disperse, gives each moment a poignancy it wouldn't otherwise have. We treasure what's temporary precisely because it's temporary. The cherry blossoms are beautiful partly because they fade. The sunset is precious partly because night follows, and our lives matter partly because they end. Deep time teaches us to hold things lightly, to appreciate what we have while we have it, knowing it won't last, to find meaning in the present rather than hoping for eternal impact, to accept that we're part of a vast cosmic story that was unfolding long before we arrived and will continue long after we're gone, and to be okay with that. The Silurian hypothesis also invites us to think about our own legacy. What will we leave behind? When future geologists examine rock layers from our era millions of years hence, if future geologists exist to do so, what will they find? They'll find the chemical signatures of our industrial activity, the carbon spike from burning fossil fuels, the radioactive isotopes from nuclear testing, the microplastics dispersed throughout sediments. They'll find evidence of mass extinctions we've caused, visible in the sudden disappearance of species from the fossil record. They'll find unusual concentrations of metals, the transformation of landscapes, possibly synthetic minerals. Will they understand what they're seeing? Will they reconstruct our civilization from these clues? Or will they attribute most of it? Thank you for listening.